So let's compare volume and pressure. So it's going to be important for you guys to be able to look at a change and say, well, the volume changed like this. That means the pressure is going to change like this, or the volume changed like this, so the temperature is going to change like this. If we decrease the volume, what's going to happen to the pressure? Feel free to unmic yourself or unmute yourself and speak up.
If you decrease the volume, I actually think it might increase the pressure because there's less space for the particles to move around, which means they might hit the walls more.
Wow, okay. Did you guys hear claim, evidence, and reasoning right there? Well done, right? I think that makes sense. I think that it would be hard to argue differently, right? So let's, spot here. Okay, there we go. So looking at this system that we have here, we want to change volume and have it affect pressure. So we don't want the temperature to change, and we don't want the number of particles to change. So on this, as long as I leave the box closed and don't pump, the particles are going to be fine. On here, you have a hold constant thing. So I'm going to say, let's hold temperature constant. I'll click that. So it's going to lock the temperature at 300. And I'm going to make some notes over here. So we have that. So volume is, I'm just going to say 10. And really the units aren't that important because volume's absolute. So volume is 10 and we're doing pressure. Let's hit pause. So 23.8. And we're going to change our volume. Let's be simple. Let's just cut the volume in half. So it's currently at 10. Our pressure was 23.8. I'm going to squeeze the box so it's about half the size. Okay. There we go. 5. So now the box is at 5. And see what happened to our pressure, 48.5. So Donovan, you said up, right? So it makes sense, right? And honestly, exactly for the same reason that Donovan said. He said, if there was less space, the particles would hit the wall more frequently, right? Which means pressure goes up. I got a chat here. When the volume decreases, there's less space for the particles to move around and they hit the wall more frequently, so pressure goes up. All right, let's look at the temperature pressure relationship. So if we increase the temperature, what do you think is going to happen to the pressure?
It will increase.
Excellent. How come? Why do you think that would make it increase?
Because the energy will go up, making them move more.
Okay, right? So again, if we think of temperature as how fast the particles are moving, right? Increase the temperature, they're going to move faster. Move faster, they should hit the wall more, right?
Numbers in here too. We're at 300 temperature. And pressure at 23.4. So let's go. Let's make it hot. 750.
So what things do we need to have not change in this system now? There's only 4. What are the other 2 besides temp and pressure?
Lock the volume of the box. I mean, just don't move it.
Yeah. Right. So we'll lock the volume so the volume stays the same. And as long as we don't add particles, the particles will stay the same. The number will stay the same. So we're at 300. We're going to go up to 750. So I'm going to add some fire. Right. And right away, pressure's starting to climb. Right. So like Caden said, if they're moving faster, they're going to hit the wall more. 5, 750. And let's see what we have here. So 58, that'll work. So excellent. Temperature up, pressure up. And the why was if the particles are moving faster, right, they're going to hit the wall more frequently. So when temperature increases, particles move faster and hit the wall more frequently, increasing pressure. Number pressure. Should we go up or down with number? What do you guys think?
Oh,
So
okay.
should we increase the particles or decrease the particles? We can do either one. Let's decrease them. Why not? So if we have fewer particles, will there be more pressure or less pressure?
Less pressure.
Less, yeah, right.
Probably because if there's less particles, they're gonna hit the wall. The one with hit the wall as much because there's less of them.
Yeah, that seems to make sense. Where we're starting at 200. Oh, okay, well, 200 particles, not very many. And a pressure of still about the same. Let's see, 23.8. And we're going to decrease it. So let's make it really small. How about 50? Let's find out. So here we want the temperature to stay the same now, right? And we also want the volume to stay the same. Am I doing that? Yeah. So I'm going to lock volume. No, excuse me. I'm going to lock temperature. And volume, if we don't move it, should stay the same. And we're going to drop particles. There's 50. Yikes. Right, so there's still, the particles are still moving at the same speed because we're still at 300 Kelvin and the box is the same size, but there's 50 instead of 200. There's a quarter the number of particles. So what do I have here? 5.8, that's not very much. So true. Number down, pressure down. And like with fewer particles, they hit the wall less frequently. With fewer particles, collisions with the wall are less frequent and pressure decreases. Don't know why it didn't work the first time. Okay. Then as we're doing these, also kind of think about real life examples of these things. Where would like number of particles and pressure exist together? Where would changing temperature and pressure exist? Where would volume and pressure exist? And now temperature and volume. So let's do temp up. We'll see if we can get the volume to go up too. So temperature up, and we're going to see what happens to volume. Do we have a prediction for that one?
I think I know the answer, but I do want to let someone else try to answer.
I think you do too. I think they do too. They just started answering. Who was that? I heard someone. Sadie, how are you doing there? Sadie, what do you think? If we increase the temperature, what will happen to the volume?
Volume, I think will stay the same.
Well, if we lock, there we go.
Oh, what did you?
Yeah, so we're going to do this, which means we're not going to change pressure and we're not going to change temperature, which means the volume is going to have to change, because if you change one of those four properties, at least one of the other four has to change, or one of the other three has to change. So
It'll increase.
yeah, right? Because on this one, when pressure isn't one of the variables, if you think of it in terms of what does the volume have to do to keep the same number of hits, right? To keep the pressure the same, then it's like, oh, when I increase the temperature, I'm going to do that right now. Pressure, I click pressure to stay the same and volume to vary. So we're going to push this up to 450. Yeah, that's what I wanted, 450. Okay, so now it's at 450. Oh, look, the volume changed. So the box got bigger, 15. If you look at this, oh, sorry. If you look at this, do you guys notice anything important between 300 to 450 and 10 to 15? I'll let you guys think about that. So, say you said the volume is going to get bigger, right? If we increase the temperature, the particles have to move faster. If the particles have to move faster, to keep the same number of hits, we need a bigger space, right? As the particles move faster, the volume has to increase to maintain the pressure. That works. And two more. Let's do these two, and we'll think of some examples here in just a second. So number volume, this one, I'm not even going to ask you guys to guess. This is like blowing up a balloon, right? If you put more air in it, it's going to get bigger. That's like really all that's going on there, right? So we'll put a number on this. Oops. Oh, I see what happened. I ran off the edge of my page. Let's do it like that. So as the number of particles increase, the volume has to increase in order to maintain the same pressure. I really like the dictate function on Word. And let's look at our last one. This is the weirdest one, I think. It's the least, this one's the least intuitive. So we're saying if we change the number of particles, how could that affect the temperature? Right? And again, if you think about what that means, it means change the number of particles, how could that affect the temperature if the pressure and the volume stay the same? So really, if you have to have the same number of hits, what's going to happen, right? Think of it that way. So let's put some numbers here. Start with 200. Wow. Okay. And we're going to put a lot more. Let's put 3 times as many, I think. All right. So if we increase the number of particles, what has to happen to the temperature to keep the same number of hits? So we want temperature to vary, but not pressure. So I'm going to click this one. Pressure is going to be locked in, 23.4. Do you guys think this is a up, like more temperature or less temperature? I heard saw some votes for a down on that. Let's find out. 600. Wow, that's a lot. Hopefully it will work. Let's see. Click, click, click. There's 400. Look, temperature's dropping and dropping and dropping. Oh, it did do 600. Yay. Slowly, but 100 Kelvin. Right. Let's put this into words really quickly here. So we're saying if we have more particles in the system, in order to maintain the pressure, they have to move slower, right? When there are more particles in the system, they must move slower to maintain the pressure. So temperature decreases. Right? And if we think about examples of these things, like volume pressure, I don't know. If you, oh, forgot to say this part. If I say volume goes down, then pressure goes up, we're also saying if volume went up, then pressure goes down, right? It's the opposite also. And you can say, you can flip it. You can say if pressure goes up, volume goes down, which is the same thing as volume goes down, pressure goes up. Because we kind of make it look like this is like one's causing the other, but really it's just two things balancing each other out, right? So if you had a balance and you'd say, when I push this side down, that side goes up, it's really the same thing, right? You're really just moving both sides at once. So here maybe an example, if you took a balloon and squeezed the balloon into a smaller space, right? You're increasing the pressure by decreasing the volume, right? Temperature, pressure, this one's pretty straightforward. If you, people kept talking about like if you put like an aerosol can in the fire, right? As it gets hotter and hotter, the particles move faster and hit the side of the can a lot harder, right? Build up the pressure, and eventually it explodes. But before it explodes, it builds a lot of pressure. And number and pressure, I always think about like a bicycle pump, or rather a bicycle tire. When you pump up a tire, right? Once the tire has air in it, like not flat, but once it has air in it, you can put more air in it, right? And it makes it harder. It makes it, which is really higher pressure, right? You're putting more pieces in there. They hit the wall harder. It stays the same size, but it gets a lot more pressure. Temperature, volume. Last hour, somebody mentioned a balloon. Like if you took a balloon and put it in the fridge, it would shrink a little bit, right? Particles move slower. If you put it outside in the sun, it would get a little bit bigger. It's pretty decent. Stick with balloons. Number, volume. If you blow up a balloon, right? The more particles, the higher the number you put in the balloon, the bigger the volume, up till it's full, right? And this one, number, temperature, is the one I feel like is the one that's kind of hard to like think of a good examples for. Really, the really good example is like an air conditioner unit or a freezer. In your air conditioning, your cooling system, it has a condenser and an evaporator, which means the evaporator means it's turning a liquid into a gas. So it's adding particles, adding number of gas to it. And the condenser does the opposite. It takes the gas and turns it back into a liquid. So essentially you're taking gas particles out of the system. So there'll be fewer number of gas particles. And the liquid underneath doesn't affect the pressure. It's just like a wall, right? It's just like having the bottom of the container. So in your refrigerator, what happens is there's a chemical, Freon or some other refrigerant, and it's liquid at first, and it goes into what's called an evaporator, which evaporates it, turns some of it into a gas. So we put more gas particles in there, which drops the temperature of the gas, and then it absorbs heat from the inside of the fridge, and it goes out of the fridge. If it's a refrigerator, to the back of the refrigerator, right? If you've ever felt behind the refrigerator, it's warm back there, because that's where the heat, or rather the gas that's carrying the heat goes. And then there's a condenser, which is the opposite, right? It takes the gas and turns it to a liquid, so it takes molecules away, which warms it up, right? And as it warms it up, there's a fan or there's coils or fins, and it takes that heat and it goes off into the room, right? So you're taking heat from the inside of the fridge and putting it on the outside. Or if it's an air conditioner, you're taking heat from the inside of your house, and somewhere outside your house, there's like a big box with a fan in it, and that's where the condenser is, and it goes out there and it blows the heat to the outside. Because to me, it always seems weird that you can change temperature by taking particles away. The other really good example of this in the opposite direction, like if you increase the temperature, you decrease the number, is a hot air balloon. If you imagine a hot air balloon, it's a big envelope of gas that's open on top and bottom, right? So if it's open on top and bottom, then the pressure inside is the same as the pressure outside, because if it wasn't, it would, if it was higher inside, the gas would leave. If it was higher outside, the gas would come in. So the pressure stays the same. But if you heat the gas up and the particles move faster, right? So temperature goes up, then instead of making the pressure go up, particles leave. So the reason that hot air balloon floats is because you heated up the gas, some of the gas left. So now you have this bubble of low density air that floats on top of the air that's outside. So, see, chemistry and hot air balloons. That's awesome. Text. So, if we have this situation, temperature went up, volume went down. Sorry, temperature went up, volume went up, excuse me. Let me ask that same question again. 300 to 450 and 10 to 15, what do those have in common? Besides they're both going up, or both going up. You guys see what those have in common?
Does it have something to do with them both being increments of 5?
Yes. Yes. Let's look at it this way. Temperature up, volume up. So if you had this like as a test question, it would tell you everything except for the final volume. So it would say a gas with a temperature of 300 Kelvin and a volume of 10 liters is heated to 450 Kelvin. What's the new volume, right? So we would be looking for this new volume, even though we know what the answer is. We know it's 15. But so what I would do is say, here's my temperature. It goes up. That means my volume has to go up. So this is the important part, that the volume's going up. So if I know the volume's going up, it's going up in proportion to what the temperature did. So my temperature went from 300 to 450. So my volume, I'm going to put my volume here, 10, I'm going to put liters, so we have a unit for it. And I'm going to multiply it by this ratio, by the ratio of temperature change. But because the volume went up, I'm going to need to multiply it by the bigger number over the smaller number. So I'm going to put 450 on top and 300 on bottom, right? The reason I put 450 on top is because I need the volume to increase, right? So because of that arrow, because it's going up, I put the big number on top. If this had been a problem where the thing I'm looking for went down, I would have put 300 on top. So 450 over 300, right, is 1.5. Does that make sense? You guys with me? 450 divided by 300 is 1.5 times 10 is 15. Yeah. And we're basically, this is you, if you know what the effect is, what effect temperature will have on volume, or pressure will have on number, or number will have on volume, those things we just went through, you'll be able to solve these problems.